Okay, question 16. An experiment is conducted in a vacuum tube whereby a stream of electrons is fired at a sample of powdered graphite. Some atoms in the graphite are 2.46 times 10 to the negative 10 meters apart, and some are 6.71 times 10 to the negative 10 meters apart. The electrons are accelerated from rest via a voltage of 2 volts before being directed through the powdered graphite. Show that the de Broglie wavelength of these electrons under these conditions is 8.68 times 10 to the negative 10 meters. Now, you haven't had a whole lot of practice doing these. I promise you're going to get more before the end of the year. But this is actually, this is probably going to become kind of bread and butter. Assuming you actually get up to this part of the exam, it's, you know, you're probably about 2 hours in at this point and starting to sweat. But, okay. So we want to show the de Broglie wavelength. So question 16a. So we want to get lambda de Broglie, and the only way we have of getting it de Broglie wavelengths, we kind of know of 2 ways at the moment. One, h over p, and the other is by comparing a diffraction pattern of an X-ray to a diffraction pattern of electrons and da-da-da, but we don't have any of that stuff here. So it's going to have to be h over p. Okay, so we've got to find p. Right? How are we going to find p? Well, we're told that they're accelerated by a 2-volt potential. So that's going to let us find the kinetic energy. Once we've found the kinetic energy, then we can find the momentum. Okay, so the kinetic energy of our electrons is going to be Q times the potential energy that they were accelerated through. So if we whenever remember, this is maybe going back to electric fields at the start of the year, remember that the amount of work done by a voltage is just the charge multiplied by the voltage. So we've got an 1 electron charge times 2 volts. So we get 2 electron volts is how much kinetic energy they're being given. But given that we want this thing in meters at the end, and so we're going to have to convert into SI units at some point. There's no real point using electron volts here, so we might as well put this into joules. Okay, so instead of writing E, I'm going to write 1.6 times 10 to the negative 19 coulombs times volts. So that's 3.2 times 10 to the negative 19 joules. A coulomb times a volt is a joule. So the kinetic energy of electrons is that. Okay, but I want their momentum. So I need to find their velocity, or I can use a quick shortcut, which is that kinetic energy is p squared on 2m. That's just a rearrangement of half mv squared, by the way. There's nothing fancy going on there. So I can get p squared equals 2 times the mass of the electron, which I'll put in that bracket in a sec, 3.2 times 10 to the negative 19 joules. And the mass of an electron, we're not given it here, but I think it's on our formula sheet. I certainly hope so. There it is. Mass of the electron, 9.1 times 10 to the negative 31. 9.1 times 10 to the negative 31 kilograms. So we find out what P is by evaluating that and then taking a square root. So let's do that. So we get, I won't write that down. And what do we got? 10 to the 31 and 10 to the negative 19. So that's 10 to the 50. So it's going to be the square root of this times 10 to the 25. Okay. Now I'm a little bit skeptical of my answer here because I'm used to getting electron momenta in the 10 to the negative 27s. So let me just double check, because you know, when you get used to certain numbers popping up more often than not, you just, if you don't see that number, just check. You know, it might still be right. So this is 10 to the negative 31 times 10 to the negative 19. that's 10 to the negative 50. So when we take a square root, it's going to be 10 to the negative 25, okay? 2 times 9 is 18, times 3 is like 54. Square root of 54 is about 7. Okay, all right, yep, yeah, all right, it seems to make sense. Maybe I'm thinking of light. Light maybe has less momentum than an electron. Makes sense, doesn't have any mass, so okay. All right, moving on. Okay, we've only got P at the moment, we don't have H, so to find lambda, the de Broglie wavelength, we got to take H, 6.63 times 10 to the negative 34 joule seconds over equals. And when we do that, so I keep closing my calculator. Why do I keep doing this? I've forgotten Planck's constant. Is it 6.63? I always get confused. 6.63 or 6.67? Where are you, Planky? Yeah, Planky. Oh, here we go. 6.63. Yeah. 6.63 divided by 7.63 equals 0.87. Now, I really probably should have kept some more decimal points there, so I hope that hasn't caused a rounding error. If it has, then I'll probably come and overwrite this video to make it seem like I was correct all along. That's a negative 10 to the 25. So we get 0.87, and 10 to the negative 4 divided by 10 to the negative 25 is 10 to the negative 9 meters. So we might want to... Okay, that'll do. 0.87 times 10 to the negative 9 meters. Does it ask for it in nanometers or anything? Okay, so I should have kept a few decimal points given that I was aiming for this. So 0.868, you can just fudge that bit. 0.868 times 10 to the negative 9 meters. Once you got to that stage there, you could just write what the answer they were telling you to get. All right, explain whether the electrons exhibit particle or wave behavior under the conditions above. Okay, so under the conditions above. So we haven't really learnt this bit that well yet. So let's you could maybe piece together what might happen from your previous knowledge, but I wouldn't be expecting everybody to get this. What we're looking at here is we have two slits which are approximately, so they're smaller than the wavelength. So notice that the slits themselves are times 10 to the negative. The slits themselves are around about the same size as the wave, and a little bit smaller, right? So they're of roughly the same order, right? So that means we are going to get wave behavior. So the way we talk about this is diffraction is roughly proportional to lambda over width. So if the widths between the atoms are, if this is, in this case, lambda over W is around about 1, or maybe you could work out what these ratios actually are, but somewhere between 1 to 5. Right. So what we're going to be getting here is significant diffraction. Right. If this lambda here were really, really small compared to the width with the widths, so if this was 10 to the negative 11 or something, or 10 to the negative 12, then we wouldn't have very much diffraction. But because this ratio here is 1-ish, we're going to get significant diffraction. We're going to get significant wave behavior. So therefore, significant wave behavior. Right. So from the atom's point of view, these look like waves. These electrons look like waves, not electrons, not particles. That's something that we'll go into a lot more detail later on. But this is basically the calculation you need. If we're trying to write a written answer to this, you would say something like, since the waves since the wavelength of the electrons is comparable to the distances between atoms, we will the electrons are best treated as waves. Now, I'm not really 100% sure why they're giving us these two different values here. Sort of maybe a more sensible version of this question would have these be wildly different. So maybe this one be 2.46 and this one be maybe times 10 to the negative 8 or something, so that one of them gives us diffraction and one of them doesn't. But they haven't really done that here. So you're going to get wave behavior for both of them. Yeah, I don't know. Not much we can say there. It's a bit of a strange question to choose those values, but that's it. I think, oh no, I thought that we were completely finished, but we're not quite. Question 17, of course, we have a ball model one. So this is the bit that you've just learnt for yourself this week. I've never told you any of this, but hopefully you can piece together some of this. Explain whether it is possible for photons of 2 electron volts to be emitted by a hydrogen atom in the n equals 3 state. So if you're in the n equals 3 state, then you're here at 12.1 electron volts of energy. And if you're going to emit a photon, then you need to jump down in energy level and release the excess. So your only options are to jump down to n equals 2, in which case, so only allowed emissions are 1.9 electron volts to n equals 3. You could go 12.1 electron volts to, I'll say that was to n equals 2, to n equals 1, the ground state. Or you could maybe do it in 2 steps, and then you'd be releasing this 1.9, but then you would also be releasing this 10.2, or 10.2 electron volts indirectly. So it's not 100% clear whether they mean emitted by the hydrogen atom in the n equals 3 state or from the n equals 3 state on its way back down to the ground state. So we'll just put that one in as a maybe. It doesn't change the structure here. So there is no transition downward corresponding to 2 electron volts. Therefore, this photon cannot be emitted. You'd probably get the marks just for saying that bit there, but I'm just a little bit worried that it's worth 2 marks here. So I just sort of wanted to cover bases by saying what photons could be emitted. Explain whether it's possible for a hydrogen atom in the n equals 3 to absorb a photon of 2 volts. So can it go from 12.1 up to 14.1? And at first you might say, well, no, there's no 14.1 electron volt energy level. But at 13.6, the atom is actually ionized. So this electron could absorb a 2 electron volt. Anything more than 1.5 electron volts, it's going to absorb it and actually be free. So for this, for part B, we'd say the electron can absorb a 2 electron volt photon. This will take its energy, that's probably not visible to you guys. This will take its energy past the ionization level, allowing it to escape. The atom. Okay, so any amount of energy that takes you past the ionization, you can absorb. So, 1.5, 1.6, 1.7, 1.8, 1.9, whatever, it doesn't matter. Once you get to that ionization energy, every possible energy is available. It's only when you're inside the atom that you have these bands of available energies. Okay, explain how the energy levels represent evidence of the dual nature of matter. Okay, so the dual nature of matter is a key word here. So what they're not looking for is the dual nature of light. So we could talk about the dual nature of light here, because we could talk about how it's only released in these little packets of energy and their photons and blah, 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 blah. But they want the dual nature of matter. So they want to know what in this story here tells us that electrons are behaving like waves. So these discrete energy levels. So discrete just means there's no continuum between them. They're chunked. These discrete energy levels, we haven't learnt this part yet, so don't feel bad if you didn't get this one. You can give yourself these 2 marks. These discrete energy levels represent standing waves of electrons in between levels we get destructive interference. No electron can be found. There. So explain how they give us evidence. Explain the energy levels. So these discrete energy levels represent standing waves. In between levels, we get destructive interference. No electron can be found there. So it's a little bit of an odd one, because there's not really anything about the particle nature of electrons here in that answer. So I wonder whether this would count as a full answer to the dual nature. I'd be interested to see the solutions. I would say the discreteness of the energy levels really only talks to the wave nature. But maybe there's a good answer for this question in the solution. So I might come back and paste over the top of this if there is. But I can't think of one, to be honest. Anyway, okay. So yeah, maybe the short answer to this question is we expect electrons to be particles. So explain how this shows that they're waves. So you just talk about standing waves, and you'll understand this in a lot more detail next week, so I won't spend too much time on it. Okay, I think the last question should just be about experimental methods. Yeah, it looks like it is. Okay. So the last question always seems to be about experimental methods these days. Question 18. Not even going to rule up my page. That's how confident I am. All right. 2 physics students undertake a practical investigation to determine the wave speed in the slinky string, blah, blah, blah. The one end of the slinky string is connected to a fixed block, and one of the students holds the other end, blah, blah, blah. The other student records the length of the slinky string and the time it takes for the electron to travel the block. Slinky string stretched so that it has a new length for the next trial. Okay, so they're stretching between trials, or between, I wouldn't call these trials, I'd call these new treatments, but anyway. So our independent variable is going to be the length of the slinky, and the time is how long the pulse takes to travel down the length of the slinky. Students produced the table below showing the calculated wave speeds. And so even though the time is increasing, it's not increasing as fast as the length. So the wave speed is actually increasing with the length of the spring. The uncertainty in the wave speed is calculated to be 0.2 meters per second. So they're probably going to ask us to do some error bars. On the axes provided below, plot a graph of wave speed, meters per second, versus spring length. Include a scale for each axis. Insert uncertainty bars for the speed values. Draw a line that best fits the data. Okay, so I'm going to pause the video here. I'm going to draw this, and then I'm going to paste it up. So, bit of movie magic here. Okay, so here's my attempt to do this graph. So a few things. Notice I've got my error bars going to zero point 0.2 centimeters, 0.2 meters per second either side of each point, as they've told me to. Just plotted out the points pretty simply. There's nothing too difficult going on here. In terms of just planning out my plot, just whatever the largest value was for each the x and the y, I just rounded that up and then made that the end of my area. So that maximizes the size that your plot's going to be, which is what you want. Well, drawing the line in, unless your data, unless you have a good reason to think that this ought to be linear for all of time and space, or for all possible lengths of the slinky, then don't draw your line of best fit poking out all the way back to the y-intercept or anything, because we don't know what would happen to the slinky as it gets really, really short. And we know for a fact that we can't make the slinky 0 length. So there's no point drawing in a line of best fit that pretends that can be the case. So we only want to draw a line, we only want to continue lines of best fit when we have a reason to believe that the sort of the basic dynamics stay the same outside of this region. And we don't have that here, so let's just not do it. We've got uncertainty bars. We've got a scale on each axis. Yep. We've got labeled axes, which aren't always labeled for us, but they are in this case. And I think we're done. We're not told we have to put X uncertainties in for length. And in fact, we're not even told how we're measuring this length. So we can't put those uncertainties in. But if we were, then we should. So I think we're done. All right. So state whether the student's hypothesis is supported or rejected. Support your answer with an explanation of the relationship between the wave speed and the length of the slinky sprint. Calculators are not required. Okay, so their hypothesis is the wave speed will remain constant for all trials. And I mean, it looks wrong. It looks wrong according to this. So specifically, I mean, this is just my preference, but I would probably draw a dotted line. I'm going to do it in grey. Nope. Wow. Be green. Okay. Microsoft Paint is an unruly beast. So I would probably draw a horizontal line in here and right next to it, hypothesis. Or maybe a family of horizontal lines. But that's not required for this. So in order to state whether the hypothesis is supported or rejected and to support my answer with an explanation, what I want to do is say what I would see if the hypothesis were supported, and then that I don't see it, okay, or that I do, or that maybe I do, okay. So if the wave speed were constant, then a horizontal line would be a possible fit for our data. No horizontal line can possibly fit through all error bars. Oh, sorry, I'm not showing you that. Here we go. Okay. You might even want to say, i.e., 2.2 meters per second plus 0.2 meters per second is less than 3.3 meters per second minus 0.2 meters per second. I.e., even if we are maximally generous with our errors and we say this one was an under measurement and this one was an over measurement, we still can't get a horizontal line to go through both of those points. Or alternatively, you could draw, sorry, I haven't got the sketch there. Alternatively, you could draw a horizontal line just sitting on the very top of this error bar and say, nah, it doesn't go through this error one at all. Okay. So therefore, the hypothesis is not supported. It is rejected. You want to mirror their language. So if they talk about supporting, not supporting, rejecting, etc., you want to say it's rejected. Okay, so it is not the idea that the wave speed is actually constant is not supported by this data, right? And you could say, well, maybe there were some mistakes in the method. And da, da, da. Well, if there were, then they should be in those error bars, right? Those if there were any other considerations here, then we would have bigger error bars than we do. So if these error bars have actually been worked out properly, then it is not possible that the wave speed is constant. Okay. With these hypothesis testing type questions, you do want to be adopting that language of, a bit like when we were talking about the wave theory earlier, that language of, if that were true, here's what we'd see, do we? Right. So these experimental hypothesis questions do have a kind of a close link to these questions, these conceptual questions that we ask around the photoelectric effect and the Young's double slit experiment. Okay, that's me done after a marathon session. I think we're at the end. Yes, excellent. Okay, all right. I'll see you later. Hopefully I don't have to go back and do too many corrections on this.